All right, good morning, e-learners. You are in for a treat today. Hey, find your seat. All right. Now I need everyone to listen. So it really starts today. Okay. I remember being in your place. You know, this was let's see, I took geometry 1980. In 1988, Miss Shanklin, my favorite math teacher of all time, she was just a very good teacher. And I sat in her geometry class, and she said, you know, something like what I'm about to tell you. We're going to do start proofs today. And I was like, oh, I'd heard from my my older sister and from other friends I had who were older than me that, you know, proofs were really hard. And I remember sitting through that first class, and it was like blah, 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 blah. Like I could follow bits and pieces, but I certainly didn't get what this was all about. I expect fully that most of you will be like that today. It's an expectation for me, the teacher, that I will have many clueless students today. What I'm trying to tell you is, we'll be okay. I don't know a way around the cluelessness. What I do know is that eventually you will get proofs. I can't say that you'll ever love proofs. Some of you will definitely love proofs, but many of you will despise these things called proofs. I said at the start of the year, for an average class, geometry, not an honors class, but an average class, my goal is to get you to fully understand proofs, to understand why proofs work, to maybe do some easy ones. But for some of you, I mean, proofs are really challenging. Proofs will not be the difference between you passing and failing geometry. Proofs will be the difference of you getting a C versus a B or A. You might get the rest of the geometry, like how to do the calculations and all that, but the proofs will be the difference between a C and a B or an A. So every proof that I put on a test is worth enough points that it will drop you one letter grade. So your goal is you got to get a B or an A without the proof, so that if you screw up the proof, because proofs are all about logic, and it's logical thinking, and that's something that's challenging to teach. Some of you will get this like this even today. I mean, literally, they'll sit there and they're like, yes, I know exactly what the next step is. Others of you will sit there and like, what? I don't even know where that's coming from. We're okay with that today, tomorrow, next week. I would say if we're in chapter 4 and you still don't understand what a proof is, we got big problems. But the logic of a proof, or being able to pick out what should be the next step, that's something that we will work on the entire year. So this is my way of trying to both put pressure and take pressure off. Putting pressure on you is saying, hey, in order for you to get a great grade in my class, you've got to be able to do a proof. But also trying to take some pressure off by saying, I fully expect some of you won't get this, especially today. So maybe it was like the second week of proofs, and the teacher finally said, okay, now you're going to do a proof by yourself. I remember I sat there with my good buddy, Jim Gillette, and I said, okay, now we got to do this stuff. And we're sitting in the library, and we kind of worked our way through a proof. And, you know, it just, for me, it kind of eventually clicked. But it was absolutely not the first day or the second day. So do not get too frustrated if you can't get these proofs today. We'll do, I think, 2 proofs, something like that. And I'm going to give you 2 proofs tonight for homework or over the weekend. Now, the 2 that I give you, and this goes through like maybe at least half of the chapter, are what are called guided proofs. They are literally going to tell you every single step. All they're going to do is erase a few keywords. And your job is to put the keywords in there. I've had students that this is really good for, they get this. I've had other students that it's like too constraining, too restrictive, and they don't get the logic part because they need to have a blank sheet of paper where they do proof. I'm the same way. I hate these proofs where they literally tell you what the steps should be instead of allowing you to freely think about what would you do next. All right, homework. Any questions on it? Yes, number 8. Number 8. Let's take a look at number 8. Number 8. 8 in Spanish is ocho. Ocho. ESPN Ocho.
I did not know that.
It's from a movie. I forget what.
That's still a thing. ESPN.
Is it?
Just looks up.
All right, number 8 says the following. It says, if the measure of AOC is 180, then angle AOC is a straight angle. Second statement, if angle AOC is a straight angle, then the measure of angle AOC is 180. So I just want you to notice that they said it one way, they took the P and the Q and they flip-flopped it, right? So both the conditional and the converse are true. What do they want you to do? Rewrite as a biconditional. Here's how that's done. You can take either statement. It doesn't matter which one. You take the first statement, erase the if, and erase the then. Where the then is, you simply replace it with the magic words if and only if. That's what makes a biconditional. So if I did it to the first statement, the measure of angle AOC is 180 degrees if and only if angle AOC is a straight angle. That's one way of saying it. If I want to do it to the second one, I erase the if, I erase the then, replace the then with the magic words if and only if. So angle AOC is a straight angle if and only if the measure of angle AOC is 180. That's how it's done. Anybody else? Yes. Number 12. Prove a counterexample to show that each statement is false. So they're telling you each statement here is false. You may use words or a diagram. So number 12 says n squared equals 5n, then n equals 5. Okay. Well, what happens if n is 0? Right? If n is 0, what's n squared? If n is 0, what's n squared?
0.
Well, what's 5 times n? 0. So therefore, n isn't 5. It could be also 0. So I gave you a counterexample.
I thought there was a 0 somewhere there, but here's what I wrote.
Yeah.
I was completely confused.
That's kind of a challenging one right there as well. Anybody else? All right. I just want to collect these today. I just want to collect those. Wes, could you collect those for me? Just grab one of the empty boxes. The rest of us, here we go. Oh, this is proofs are fun.
Are they?
They are. Proofs are the only thing that actually gets me excited about geometry. The rest of it is fun, but proofs get me excited. All right. Next quiz, Wednesday, next quiz. Hey, that's not a lot of homework, is it? Each one of these is a proof. So these are 5 proofs tonight for homework. 5 proofs for homework. Today in class, we're going to do 2 proofs. Just 2. For today in class, we're going to do 2 proofs.
From our homework.
No, oh, gotcha. Good one. If we have time, we'll pick one of the first 3 we could do in class. Okay. All right. So had a little bit of a speech there. You should be a little bit anxious right now. This is definitely a class you want to pay attention. Okay. If the only thing you get from this class of what a proof visually looks like, we're good. If that's the only thing you get. If the only thing you get from this class is the fact that you have to do this thing logically, we're good to go. Right? We will do an entire year's worth of proofs. Nearly every class, I'm trying to think of constructions we don't do a proof. Nearly every class we do, we will do more than 1 proof in class. Almost always for homework, we'll have at least 1 proof. All right, here we go. Wait, it doesn't say the word proof. It says properties from algebra. Well, I would have named this an intro to proofs. In most geometry books, the first time they do, they call it intro to proofs, but this one doesn't. All right, here we go. I need you to write this down in your book of truth. So in your notebook, where you had all your postulates and theorems, this is where this should go. None of these are theorems or postulate. Technically, we call these properties. I would say they're on the same level as a definition. Okay? So every one of these you already know. Every one of these you already know, with exception of one, something called the transitive property. Okay? And I'll show you what that is. So we're going to write down something we already know. right? Remember, we prove everything in algebra or in geometry. Let's see, we've already done some basic definitions, a couple postulates, and we've talked about addition, subtraction, multiplication, division, and I said, well, that also would apply to exponents as well, too. What we haven't talked about is solving equations, like what allows us to solve equations. So let's talk about that. The first property, this is going to be weird speak. I need you to write this down at the very top. A, B, and C are all going to be a real number. A real number are, well, every number you can think of other than unreal numbers, which, anybody know what's an unreal number? Okay. You will learn about this next year in Algebra 2. We don't call them unreal numbers. We call them imaginary numbers. Imaginary numbers is the answer to this problem. What's the square root of -9? What number multiplied by itself is negative? Well, you don't know a number like that, right? Right now, we say this has no answers. And in geometry, we still say it has no answers. Next year, you find out this actually does have an answer. You type this into your calculator right now, your calculator will say error, unless you press a special button that says calculator, you are allowed to do imaginary numbers, and then your calculator tells you the answer. If you're curious, I'll show you at the end of class. All right, the first property is called the addition property. Do you remember back when your first algebra teacher or your pre-algebra teacher, that would be me, by the way, said you can add anything you want as long as you do it to both sides, to the other side. So that's all this says. It's called the addition property. And it says that if you have an equation, you can add whatever you want as long as you do it to both sides. That's all it says. You're like, do I really need to write this down? Yes. This will be an answer to a proof tonight. Literally, the thing that says addition property. Now, if we have addition property, we must have a subtraction. Okay, so same idea. You are allowed to subtract anything as long as you subtract it from both sides. Do you think it's important to write this thing, or is it important to write this stuff? I would say so, unless it's locked in your brain that you know what the addition property. Addition property just says you can add anything you want to an equation as long as you do it to both sides. If you need to write this, great. But you absolutely positively, this is what you got to have memorized or in your book of truth. It'll make more sense at the end of class. It certainly won't make much sense right now. If we have the addition property, the subtraction property, we also must have the
multiplication and division.
Okay, I'll give you both. The multiplication and division properties say exactly what you would think they'd say. You are allowed to multiply anything you want to an equation as long as you do it to both sides. That's supposed to be an R. It's just cut off a little bit. Or sorry, that's supposed to be a C. It's just cut off a little bit. So this is a C. And I apologize. This is very small because we're going to fill this page up of properties. But all of these properties you've used before. Division property says you can divide anything you want from both sides as long as you do it to both sides. So we have the addition, subtraction, multiplication, division property. I don't have my slides in front of me. What's next? All right. I'll pause and let you guys catch up. It is more important that you understand the name of the property and what it does than this stuff right here. That's using the fact that A, B, and C are real numbers, and to give you an example. In geometry, you can solve an equation. What allows you to solve the equation? These properties right here. I mean, that's how you solve equations. But we had to prove it, or we had to at least define it. Yes? I said at the end of class. I'll tell you at the end of class. Micah can't handle the fact that he can do imaginary numbers and he wants to do it right now. Okay, the next three properties, they're common sense except for one of them, right? I'm going to do them slowly, but they're very common sense. If I wrote a number, give me any number.
5.
Is 5 equal to 5?
Yes.
We have a property for this.
Why?
Imagine you are standing in front of a mirror. What do you see? You see yourself. This is why this property is called the reflexive property. The reflective property says this crazy thing is a reflexive property just says says that 5 is equal to 5. You're like, well, that's the dumbest thing I've ever seen. When would I ever use this? This is one of the most used properties in geometry, the reflexive property. We will use this literally 100 times this year, the reflexive property. Like, I don't even understand why that would even occur. Well, you will when we do some examples. Reflexive property just says something is equal to itself. That's a pretty easy one. And we will use it enough that you won't have to memorize that because we're going to use it so frequently. The next, and by the way, this one is in yellow. I'll explain it when we get to the bottom. The next property, once again, it's kind of an obvious one. If x equals y, is there another way of writing this?
Y equals X.
That has a name, and that's the next property. See what I did? I just swapped the orders around.
Is it called the swapping?
It should be called the swapping property, right? But instead, it starts with an S. It's called the symmetrical property.
What the heck?
The symmetrical property says if A equals B, then B equals A. We will use the symmetrical property occasionally, but not as much as the reflexive property. Symmetrical property just says if A equals B, then B equals A. Am I going too fast? You guys keeping up? This is the painful part. Once we got like 3 more to go, and then it stops being painful. Oh no, I should say, then we do a proof. Then it becomes really painful. Okay, so the next one is this. Check it out. You have a dollar bill in your pocket. I have a dollar bill in my pocket. And she has a dollar, and I'm standing in the middle. Does his dollar equal my dollar? Does my dollar equal her dollar? So does her dollar equal his dollar? That's what this next property says. That whatever he has is the same as what I got, and whatever I got is the same as what she got, right? Then they got the same thing. There's bad grammar there. All right, that is called the transitive property. We will use the transitive property a lot. But that's all it says. Chris has something and I have the same thing. And I have something and Jenna has the same thing. Then Chris and Jenna have the same thing. Transitive property can go further. You know, if A equals B and B equals C and C equals D and E equals F, then A equals F. But transitive property is always written with 3 things. But you could have more than 3. So reflexive, symmetrical, and the transitive property are all in yellow. Not these, 1, 2, 3, 4, but the ones in yellow, we can also erase the equal symbol and put a congruency symbol. So somewhere off to the side, you need to put that these, you could also say the reflexive property, not of equations, but of congruency, right? So the yellow ones also, we can erase the equal sign and put a congruency symbol. If A is congruent to A, then A is congruent to A. That's the reflexive property. If A is congruent to B, then B is congruent to A. Transitive property, if A is congruent to B and B is congruent to C, then A is congruent to C. The next one we have used in Algebra 1, and it is probably the second, other than reflexive, the second most used property. It's called the substitution property. That says if you have 2 things that are equal, you can substitute one for the other. We will use substitution property today a bunch of times. A bunch of times. Today, we will use the substitution property more than any other property. This year in algebra, you will use the substitution property over and over and over again. And you'll become so accustomed to saying, oh yeah, just do a substitution right there, that you want to be thinking about this. In fact, we will get lazy and not even use the word property. We will just write substitution. We will get so lazy that we won't write reflexive property, we'll just write reflexive. Because we use substitution and reflexive a lot. This is a lot of stuff in one day. The yellow ones are new. The other ones are old hat. Now, I took this all from page, 37? There are some more properties, but I didn't like the book. I put them on there. I could equally put them right here. So you don't need to go to a new page. but there's a couple other properties that we need to put in it. We okay? All right. Just remember the ones in yellow, you can also use it with congruency. This one you know, right? The distributive property. So we are allowed to use the distributive property. If you just want to write the word on the bottom here and write distributive property, you can. There's no distributive property of congruence though. So we have the distributive property. Apparently it gets its own box in the book. I'm not sure why. They could have equally put it on page 37, but they didn't. They put it on the next page.
Because this is a book for logic, and it's not logic.
Yeah, I agree. This one wasn't that logical. So everyone knows distributive property, you use it all the time, yes? We don't even think about it now. 3 years ago when you were first introduced to distributive property, it was a big challenging thing. So we now have a lot of stuff in our book of knowledge. We got, 9 postulates, we got 3 theorems, we got some definitions, and now we have all of these properties. We have enough knowledge that we can do these things called proofs. The goal of a proof is to prove something. Okay, so proofs. Proofs. Box 1 is empty. So I need to write down everything in this box. A proof is a logical way of showing that a conjecture is true. Yesterday I said, well, in geometry, we're not going to write false conjectures. That's true. But we also have to prove to you that the conjecture is true. The way we do that is this thing called a PROOFS, a proof. Right? I said that really badly. The way we do that is a PROOF, a proof. A proof is the way that we prove things in geometry. There are many different types of proofs. We will be learning 4 of them four or 5 of them this year. Today we're learning 1. We've already seen an informal proof, that was yesterday. Today we will do what's called a formal proof. It has a visual look to it. Okay? The first one is called a 2-column proof. And for centuries, we've taught students using 2-column proofs. I made that up. I don't even know if that's true. For decades, that part I know is true. We've used a 2-column proof. First method is called a 2-column proof. You don't even need to remember it, right? We're just going to do it. But it's called a 2-column proof. All right. Here's your 2 columns. You see them? 1, 2. On the left side, we were going to have statements. On the right side, we're going to have the reasons that allow you to make that statement. The reasons must be true. A reason is not, well, because. A reason is not, well, I thought it was true. Reasons come from your book of truth. The only thing that you can put for reasons is something from your notebook. If it's not your notebook, you can't put it as a reason. The only thing we put for reasons are something from your book of truth. That's going to include theorems, postulates, definitions, the properties. Okay? The statements you absolutely make up. You're going to make a statement, a bold statement, and you're going to prove it, or you're going to give a reason from your book of truth. This should make no sense to you right now, but it will. Okay? You will be given 2 things. No pun intended, given. You'll be given 2 things at the start of a proof. You can kind of see them right now on your piece of paper. The first thing you'll be given is literally the word given. A given is the start of the proof. It's what you're allowed to assume. The prove is what you're trying to get to. The given is your start. Your prove is your end. It's like a crossword puzzle. You get all these things. You have a starting point. You know your end when it's all filled in. For a proof, the given is how you start. The prove is how you end it. Once again, this probably doesn't make any sense. Here's you're writing this all down, yes? The given is your starting point. The proof is your ending. You're done when you get to the prove. Unfortunately, we have to write this down. It doesn't make sense until we do one. You say the same thing. Good? All right. This is the one that is the key to a proof. All your statements follow a logical sequence. You can't pick and choose. Well, I want to jump way over there or then jump over here. One statement follows the next statement logically. This is the hardest one to understand right now, but when we actually do one, you'll see that it kind of makes sense. Very next slide. Very next slide. All right. That's what a two-column, well, that's what proofs do, and this is what a two-column proof looks like. Notice on the sheet of paper that I handed you, boy, that takes up a lot of space, right, to do a proof. So.
All right, we're going to throw Kelsey in the deep end. No swimming, no floor. You can video this. That's 9 feet here. 9 feet. Okay? And she's going to swim back by herself.
Where is
Ready,
she?
Kelsey? Here we go.
So that's what I'm about to do to you, is throw you in the deep end. Hopefully you don't drown. Here we go.
That was just impressive.
So,
She was happy to go in.
we're going to, instead of doing a geometry proof, we're going to do an algebra proof. Why? Because you already know the answer to the algebra stuff. So I'm going to do an algebra proof, right? Because you'll be able to follow the logic very easy. You already know the logic. The geometry one, you don't. So here goes the start. So this is called two-column proof. So a two-column proof is you're given a given. This is your starting point. This is how this problem ends. So all I'm really asking you to do is solve this equation. How many people here right now could solve this equation? Better be everyone, right? You could solve this. There's the answer, by the way. Well, how do you prove it? We prove it by our book of knowledge, right? We prove it by doing what's called a two-column proof. There's my two-column proof. No, you don't have to write the word statements or reasons. I'm putting that there for the first one. You're just going to draw two columns. Your statements are going to go over here, and your reasons are going to go over here. From the previous slide, where do we start? We start with the given. The given is where you start. So right here, my first statement will always be the given. So I write the given. Well, what's my reason for stating this? It's the given. It's the easiest one to do. All of your proofs will look like this. You will take the given, you'll write it as your first statement, the reason for it, because it's given to you. We will continue this proof until one of your statements says this. This is your start, this is your finish. Okay, we're in algebra world, and you're all in a comfortable world. What do you do to solve this? What's my first step? Can we all agree that we're going to add 5 to both sides? What would you get after you added 5 to both sides? Tell me what you would get after you added 5 to both sides. 4x equals 3, right? Oh, this is my finish. That's where I'm going. So my next step will be 4x equals 3. You don't have to write. I'm just showing you that this would be the last step. What's the reason? What allowed me to do that from your book of truth? What allowed me to add 5 to both sides?
Addition property.
Remember when I said there would be some kid that gets this immediately and other kids are still thinking? So from the book of truth, what allows me to add the same thing to both sides? That's my reason. How do I go from this step to this step? How do I go from this step to this step?
Divide.
Both sides by, what's the reason that allows me to do that? Are we done? Did we start with the given and did we get to the proof?
Yes, sir.
Okay. In geometry, when you're done with the proof, we have a symbol or abbreviation that says, I'm done. You have to put this. You can either put a little tiny square or you can put in Latin QED. QED means quad erratum demonstrandum. It means that which was to be shown. Well, that which was to be shown was, I was given this, I was supposed to show that x equals 3/4. I did it. Boom, done. You can either put a box or QED. I like QED. In college, I only put the box, and then I started, well, I kind of like QED. Okay, you just did your first proof. And you're like, wait a minute, no, I just solved an equation. Yes, remember, I was showing you a proof by using an algebra example. Obviously, in front of you right now are 2 geometry proofs.
Oh, really?
So here we go. Box 2, we're all going to do this together.
Yes, sir.
So the first thing I want you to do, huge, in box 2, give me 2 columns. Like that. You don't have to put the word statements or reasons. By maybe next class, I won't have the word statements and reasons. I'm just going to have columns. Has everybody got that on your paper?
Yes, sir.
Now, for the most part, like which side needs to be bigger, you'll get a feel for it, right? But I will say this, you got to give yourself space when you do proofs. Space, when you do a proof, it's typically a half a page, right? Maybe a full page if it's a long proof. What's my first statement going to be always in a geometry proof? I'm going to, this is painful. I'm going to rewrite that sucker. Why? It's right there. No, you got to rewrite it. So you're going to rewrite it. What's the reason? It's the given. Now, we're going to talk about logic. You're going to take a step back. Typically, not always, but 90% of the time they give you a diagram. Sometimes they don't, but 90% of the time you get a diagram. We're going to take the given. We're going to think about the diagram. What does it mean? Look at the diagram. Tell me something that you see on the diagram, either on your paper or on the board. Tell me something that you see.
We have 4 lines.
I don't have 4 line segments. I have 2 line segments. This one and this one. That intersect. Go ahead, Madison. Madison. Sorry, Cadence. Notice I got 2 tick marks here. I got 2 tick marks here. Not on the same segment, right? What else do you see? What else? I see that this one and this one are congruent. That's what the 1 tick mark means. Anything else you notice? And there might be nothing else. Somebody said that they intersect at 1 point. I agree. Yeah. Anything else? It's kind of like maybe later when we start thinking about angles, you might be able to say something about angles, but for right now, nothing. That's all I've got. How do I know I'm done with this sucker? I got to somehow get this as my last statement. This has to be my last statement. Okay? Here comes the hard part. I would not expect anyone to know what to do at this point. You will. Oh, do you know it? Or don't? You can't look at the book. Okay. Good job, Chandler. All right. Notice what this says. What does it say? I got an RT and a PQ. Do you see any RT or PQ right here? Where? Do you see any RT or PQ right here? I don't. So somehow I need to get an RT in there. So here's your first logic technique. If I need an RT, I better say RT. Like I literally got to write RT. So I go back to my picture and I say, well, where's RT? Where is RT? Can you tell me anything that you know about RT? Because I want to have a statement that says RT something. Can you tell me something about RT from the Book of Truth? It does intersect. So maybe I can have a statement that says RT intersects. By the way, that's part of our given. So it's already there. What else can I say about RT? Anything. If you look at your book, I don't, because it kind of gives it away. Say again? It equals 180 degrees. We could use that from our Book of Truth, right? Does this have anything to do with angle measurements? What I'm saying, does this say, though, prove that RT something equals 180 degrees? It doesn't. But maybe that might be the only thing we know. That would certainly get us into an RT. Well, there's one other thing that I can say about RT. It comes from postulate 2. You might want to flip through your book. What's postulate 2?
RS plus ST equals RT.
He's giving you laser beams from his eyes because he stole his thunder. So what he just said was postulate 2, which is called the segment addition postulate, says what? A big segment is made up of the 2 smaller sections. So how would you write that, Harris? How do I write the big is made up of the 2 small? Okay. The big is made up of this one and this one, right? Subtracted, added, multiplied together, what? The big one is made up of this one and this one. What? Subtracted, added, multiplied, what? added together. So I can write RT. I need to have an RT. So I could write that RT is equal to this plus this, yes? Well, I also need to get a PQ. What could I also say? That PQ is equal to this plus this, so let's do that. Notice I have two statements here, semicolon. You can put as many statements as you want if the reason is the same. You can have as many statements as you want if the reason is the same. I generally don't see more than 2, but I mean, you could have 10. You should be lost on why I'm making this statement. You shouldn't be lost on the statement itself, right? The logic of the statement should make sense. Why I'm doing it obviously might not make sense. What was my reason for this? Postulate 2. Notice, did I say postulate 2? No, because after next week I'm going to forget that it's postulate 2, but I'm going to remember its name. So you can either put postulate 2 or segment addition postulate. For the ones that have the name, it's convenient. Because you won't remember, oh, that's postulate 2. You might remember this one. The logic of it was this. If this is my ending point, I better have an RT and a PQ. Well, none of these given statements says anything about RT or PQ. Okay. Here comes the hardest one. All right. Once again, you're not going to panic if you don't get the logic. Right? You're going to panic because you don't understand what I write. What's that say? Okay. What's this say? You agree they both say the same thing? They're reflexive, right? What does RS equal? So if I see any RS by substitution, I could put PS. What's this say? What's this say? So if I see any ST, I could write, I'm going to do a double substitution. I'm going to substitute for RS, PS. I'm going to substitute for ST, SQ. Write that down, and I'll show you why I'm doing this. So RT equals, well, not RS, because RS equals PS, plus ST, but not ST, but SQ. What allowed me to do that? What allowed me to do that? Substitution property. Like I said, by a month from now, you're going to be writing SUB because it's too much to write. You can't write substitution property now and for the next test as well too. By chapter 4, I'll say, yeah, you can go ahead and use some abbreviations. All right. Why did I do this? Why did I do this? Well, once again, I need to show that RT equals PQ. Here comes the magic. You ready? What's this say now?
PQ.
Do you know where I'm going, Karis? Oh. Usually when somebody says, oh, I see it. What does this say?
PQ.
Hold that. What does this say right now? What's that say? And what does this equal? Boom! We're done. What allowed me to do that? What allowed me to do that? Not the addition property. Substitution. QED, baby. There's your first geometry proof. Now, tonight for homework, you're going to have 3 algebra proofs. You're just going to solve the equation, cite the reason, you'll get those. That's 1 through 3. You will have 2 geometry proofs. Let me finish. Sid. You will have 2 geometry proofs. Everyone open up your book. Everybody open up their books. Look at questions 7 and 8. Look at 7 and 8. 41, sorry, 41. Look at page 41 at the bottom. Questions 1, 2, and 3, it's an algebra proof. Just cite the reasons, you'll be good to go. Questions 7 and 8 are 2 proofs. They give you all the statements. They give you none of the reasons. You will have to look at what they state for the statements and come up with the reasons. Okay? Always remember, I'll give you the first answer on number 8. The first statement is missing. Guess what the first statement always is? The given. So there you go. There's your first answer. What's the last statement always? What you're trying to prove. So there's all the statements done for question number 8. You just got to come up with the reasons now. Give it a shot. I absolutely 100% do not expect all of you to come back saying, oh, I got proofs. But give it a shot. We're going to break this into a 2-day class. So this was half. We'll do the other half on Monday. Have a good weekend. Do something fun.
Like geometry.
So as long as you understand that it's 2 columns, you start with the given, you end with that, and then the reasons come from your book of truth. That's the whole class. Getting those things, don't think that 1 minute that any of that logic right there, I would expect anyone in this class to be able to come up with themselves. Absolutely not. Not at this point. Later on, yes, but we're not there yet. All right, e-learners. I will see you. We're going to start the Microsoft Teams, so we'll be doing this all through Microsoft Teams. I'll be posting a class every single day and the video. If you need any assistance, go ahead and send me an email, and I'll see you guys next class.